Welcome back. Today, we are going to peel back the layers on one of the most important pieces of technology in modern software, containers. You hear that word all the time, right? But what even is a container? Well, let's get into it, because I guarantee you the answer is not what you think. See, here's the secret. A container isn't actually a thing, not in the way a file or a folder is a thing. As this quote gets at, it's really just an illusion. It's a clever trick that the Linux kernel plays on a computer process to make that process think it's all alone on its own private machine. And today, we're going to pick that illusion apart. But before we get into how that illusion is built, we've got to tackle the big question everyone asks. If it's an isolated environment, isn't that just a virtual machine? The answer is a big, fat no. And that difference is the key to understanding everything else. So let's start right there with that core distinction, because this isn't some minor technical detail. This is the fundamental fork in the road that decides everything about how these two things perform, how big they are, and how fast they run. Okay, here's the absolute heart of the matter. A virtual machine, or VM, has to pretend to be an entire computer. You have a piece of software called a hypervisor that creates fake hardware, and then you have to install a whole new, complete operating system right on top of it. A container, it does none of that. It's just a normal process running on the host, and it shares the host's Linux kernel directly. It doesn't need its own kernel. It's just been put inside a very special, very convincing box. And this is where you really feel that difference. A VM has to boot up an entire operating system, so it can take minutes to start. A container? It starts up as fast as any other program. We're talking milliseconds. A VM needs gigabytes of disk space for its OS. A container just needs maybe a few megabytes for the app and its libraries. This all adds up to basically native bare metal performance, and it means you can pack 3 to 4 times more applications onto the exact same server. The efficiency is just wow. It's staggering. All right, so if a container is really just a process, how in the world do we create that powerful illusion of isolation? Well, the first part of the trick is what I like to call the walls. In the Linux world, these are called namespaces, and their entire job is to control what a process is allowed to see. Think of it this way. Namespaces create a split reality right inside the kernel. A process that's running inside a namespace gets its own private, custom view of the system. It's like putting a set of blinders on the process, so it can't see any of its neighbors. And if you can't see anyone else, you start to believe you're the only one there. So let's look at a real example, the PID or process ID namespace. On any normal Linux system, you have one single list of all the running processes, starting with the famous PID1. But inside a container, this namespace gives the process its own private list. The very first process that starts up inside that container, from its point of view, it's PID1. So if you run a command like ps inside, you'll only see the processes for that one container. Everything else on the host is totally invisible. Then you've got the network namespace, and this one is just unbelievably powerful. It gives the container its own completely separate network stack. We're talking its own IP address, its own routing tables, its own set of ports. This is exactly how you can run, say, 10 different web servers on the same machine and have all of them listen on port 80 without any conflicts. It's because each one is living in its own little network bubble. Now, rounding it out, the mount namespace gives the process a private view of the computer's files. The container runtime uses a neat little trick to swap out the host's root file system with the one from the container image. This basically jails the container. So when it looks at the root directory, it doesn't see the host's files, it sees its own little world, whether that's Ubuntu or Alpine or whatever the image is built on. So namespaces build the walls. They control what a container can see. But that's only half the story. I mean, a process that can't see anything could still go crazy and use up 100% of the CPU, right? Crashing the whole server. So we need some rules. And that's the job of control groups, or cgroups. They limit what process can use. Groups are the answer to a question that, let's be honest, every single developer has run into. What happens when your application has a memory leak or gets a sudden spike in traffic and it tries to use way more memory than it's supposed to? Well, the answer you often get is this mysterious number. Your container just dies. And the only clue you have is exit code 137. What on earth is that? It means the C group did exactly what it was told to do. See, exit code 137 is really two numbers combined. It's 128 plus the signal number 9, which is sigkill. The kernel's out-of-memory killer, which was following the rules set by the C group's memory limit, jumped in and terminated that greedy process to protect the host machine. So it's not a crash, it's an enforcement action. Cgroups are basically the resource police for your containers. Okay, we've got the walls from namespaces, and we've got the rules from cgroups. Now we need the actual stuff inside the container. The files, the libraries, the application itself. This is the blueprint for the container's world, and it's built on a really, really efficient idea called layered file systems. Now, containers use this brilliant trick to keep from wasting tons of disk space. When a container starts, its world is made of these read-only image layers. If the container just needs to read a file, no problem, it reads it straight from that layer. But the second it tries to write to a file, that's when the magic happens. The kernel steps in, makes a quick copy of that one specific file up to a new writable layer that belongs only to that container, and then the write happens on the copy. The original image is never, ever touched. This whole system is called copy on write, and it's the reason you can run 100 containers from the exact same image without using 100 times the disk space. So we have all our pieces. We have namespaces for the walls, groups for the rules, and a layered file system for the blueprint. But something has to actually take all these pieces and assemble them in the right way. We need a conductor for our little orchestra of kernel features, and that is the role of the container runtime. When you type a command like docker run, you're kicking off what is basically a sophisticated relay race. Your command line tool talks to a high-level manager, like containerd, which gets the image and all the settings ready. Then, containerd calls a small, low-level tool called runc, whose only job is to talk to the kernel and create the namespaces and cgroups. And then, and this is the critical part, runc exits and hands off the running container to a tiny little shim process. This whole handoff system is why modern container platforms are so stable. You can literally restart the main Docker service without ever killing your running containers. All right, we've taken the illusion apart. We've seen how it's built piece by piece. Now it's time to talk about the truth. What are the incredible benefits of this model? And what are the absolutely critical risks that you have to understand to use it safely? I mean, the benefits are just undeniable. They've totally reshaped how we build software. The incredible speed makes things like serverless computing possible. The density means you can run way more apps on less hardware, saving a ton of money. And the portability, packaging your app up with its entire environment, that finally solves the age-old, well, it works on my machine problem. You get consistency all the way from your laptop into production. But, and this is probably the single most important thing to take away from all of this, a container's greatest strength, that shared kernel, is also its single biggest weakness. Look, the isolation we've been talking about is amazing for preventing containers from accidentally tripping over each other. It is not a security boundary designed to stop a motivated attacker. Because every single container is talking to the exact same kernel, if there's a vulnerability in that kernel, an attacker could exploit it from inside just one container and potentially take over the entire host machine and every other container on it. So in the end, a container is a useful lie. It's a powerful and efficient illusion that the kernel tells to a process, and it gives us all this incredible speed and portability, but it's an illusion that comes with very real trade-offs. So now that you know the truth behind the magic, you know about the namespaces, the cgroups, and that all-important shared kernel, the real question is, how will that deeper understanding change the way you build, deploy, and secure your own application?